everyone, in this video we're going to be working on the week 1 notes for Math 114. These notes that I'm looking at right now, this document is what you are going to find in your workbook that you purchased from the bookstore on page 1. So you're going to want to get that out, flip to page 1 and get yourself ready to go through these guided notes with this video. And you're also probably going to want your calculator. You don't necessarily need it for this first video, but for some mental math, you may want it. So we're going to get started. The first thing I want you to do is write this definition right here at the top of the page of variable. Okay, a variable is simply a letter, any letter that represents. So the thing that just happened right there, it's going to happen a lot, so I'm kind of glad that it happened right away. When I'm writing, I'm right-handed, and you see this thing off to the side? It kind of scrolls around, so if my hand accidentally bumps a different page, it'll bump down. I'm just going to show you it and own it right now because it's going to happen a lot. Okay, so variable is a letter that represents, look, there we go, that represents a number. Okay, so the typical variable that you're used to working with is x, maybe even y as well, but more likely than not, it's x, and it's a letter that represents a number. So when you have an equation or an expression or anything with an x in it, you're typically solving for that letter or simplifying something down with it, but it just is a placeholder for a number, okay? We're going to get a lot into solving for x later on. What we're going to be doing to start, especially for most of week 1 notes, is kind of going over some of the basics that you need to know. Like, for example, the definition of a variable. It's just a letter that represents a number that you're ultimately going to be finding later on in this semester. But for now, that's all you need to know about it. What we're going to get into now is combining like terms. So before we can start combining like terms, you need to know what a like term is. So a like term is essentially terms with the same variable and exponent. So again, like terms are terms with the same variable, which means letter, and exponent. So just some quick examples off to the side here. 2x and 3x are like terms because they have the same variable, they're both using an x, and they have the same exponent. An exponent is like, for example, if I have 2x squared, this number right here is an exponent. Because these ones don't have an exponent written, they technically have an imaginary one for their exponents. You don't ever need to write them in, but they do have the same exponent. It's implied as they both don't have one written. If you have 2x and let's say 3x squared, those are no longer like terms because even though they have the same variable, they both have an x in their term, this one has an x squared, making it not like terms. Okay, so let's do some more examples in the 4 questions that are to come. So for the directions, it says, for the following example, simplify by combining like terms. So I have to look for like terms to start, and I'm going to jump right into number 1. So I have 3x plus 5x plus 2x minus 4x. To start, terms are separated by addition and subtraction. So this one has 1, 2, 3, 4 terms. If you notice, they all have the letter x, which is great, and they also all don't have an exponent written, which means they are like terms because they all have that imaginary one of an exponent. It's not written, but because it's not written, that means it's implied that they are all the same. So these are all like terms. So what we're going to do to simplify this now is to just combine the numbers. So 3x plus 5x, combining these two to start, is 8x, plus 2x is going to be 10x, minus 4x is going to get me a total of 6x. Now notice the x just carries over. I love to use cookies as an example with like terms. This is like saying 3 cookies plus 5 cookies plus 2 cookies minus 4 cookies. Your answer has to be labeled with cookies. Okay, I know it's a stupid example, but I hope it kind of helps you understand when you're combining like terms, the letter just carries along. As they're cookies. Okay, next one's a little bit tougher because we have some different like terms involved. So the first term I see is a 3x squared. That can only be combined with other x squareds, and there's only one other x squared term, and it's that 1x squared on the end. Now I boxed in my like terms to show you this very important idea right here, and it's that minus sign. So notice, again, I boxed in my like terms, but when I created the box around the 1x squared, I included the sign before it, that minus sign, or a negative even if you want to think of it that way. You can think of it either way. But you have to include that because that tells you what to do. When you're combining 3x squared and a negative 1x squared, that's going to get you 2x squared. Or like I said, you can look at it either way. 3x squared minus 1x squared is still 2x squared. Okay, and I'm not done. I have more to combine. So I have a positive 5x and a negative 2x. When you combine those together, 5 minus 2, or in other words, 5 plus a negative 2, whichever way you look at it, is going to be a positive 3, and the x, or the cookies, carry over. Now you might be looking at this answer wondering if it's completely simplified, like the directions say we need to simplify. It is, because x squared and x are not like terms. So you cannot simplify that any further by combining any more. They are as combined as they can be, which means it's as simplified as it can get. All right, for number 3, first thing I see is 3x. So I'm going to combine that with all of my other x's, not x squareds, just x's. So I have another x right here. It's a plus 7x, and that's the only other x in the problem. So I just combined 3x plus 7x. That gets me 10x. And then I move along to the next one. The next term I see is a minus 5y. The only other term that has a y to combine this to is a positive 6y. This is where you might want to use your calculator. If you're not so good with combining positives and negatives, I want to clear this up right away. So this is a negative 5. This button right here is not the negative. That is the minus sign. That won't work. This down here is your negative symbol. That's what you want to use for your negative. So negative 5 plus 6 gets me 1. Okay, big difference between the minus and the negative sign. I just want to clear that up right in the beginning of the course. Okay, so negative 5 plus 6, when I combine them, I get a plus 1. So I'm going to write plus 1y. And then that last term there is a plus 5z. There's nothing to combine it to, but it is still part of the expression, so I'm going to bring it down. Something else I'd like to just kind of go over with the way that I do things. This is the way I make my z because I don't want to confuse it with my 2. I know they look kind of similar, so I just draw a line through my z. Okay, something else you might be wondering about this question is this term right here. You don't have to include the 1 before the number. You could write this as 10x plus y plus 5z. It's the same thing, kind of like the imaginary exponents that we had up here, but it's just the imaginary. It's called a coefficient, the number in front of your variable. Either of those answers is perfectly fine. All right, and then our last combining like terms example is a 5x plus a 7y. There are no like terms to combine here. Because there's no like terms, I can't simplify it. This actually is your answer. Just kind of a trick question in there. They do have the same exponents, but not the same letter. I didn't silence my phone for class. All right, the next section is order of operations. So order of operations is when you're trying to simplify examples like 5 through 10. Notice they have addition, subtraction, exponents, division, multiplication, a whole variety of these operations. You need to know what order to do them in to get the correct answer. Okay, it's not just whatever one looks easiest, go to that first. You have to follow this order. You might have heard Pemdas before. So what they stand for mathematically, the P stands for parentheses. Do you know how many times I've taught this and I still don't know how to spell parentheses? I'm guessing. There's parentheses. E is exponents. M is multiply. D is divide. A is add. And S is subtract. All right, so that is a lot to remember. Like, you can think of the word PEMDAS. That's probably the easiest way to think about it. If you can't remember the word PEMDAS, you may be able to think of it as the saying, please excuse. So like please for P, excuse E, my dear Aunt Sally. That's how they teach it at a lot of high schools. So that might be something that you've heard before. Instead of remembering the word PEMDAS, just think of the letter in PEMDAS, and it stands for please excuse my dear Aunt Sally. I heard an even better one a couple of years ago. It's please excuse my dope ass swag. So that one's definitely more fun. Whichever, like, it does not matter. However you want to remember the order, that's your order of operations. Use that swag. All right. So now we're going to do some examples based on this. But before we do, I want to go over, again, just some specifics with the order. So you absolutely always start with P, which is parentheses. If they have parentheses, you follow that rule. If they don't, you don't. So what I mean by parentheses is like this right here in number 8. See how there's parentheses and there's something happening in the parentheses? Even though it's addition and that step's not until here, the parentheses tell you that you have to do that first. So that's what it means by parentheses. Okay, something else you might want to know about parentheses is you might see something like this, like 2 parentheses 5 plus 6. Just pulling that out of thin air, there's no significance to it. This is not parentheses. See how there's nothing happening in the parentheses for you to do? Those parentheses don't stand for this step of parentheses to start with. What those parentheses actually represent is multiplication. There's a few different ways to signify multiplication. One of them is this dot that you also see in number 8. That'll come up a lot if you look at some of the other examples. I think there's like 4 or 5 of them. But you can also see it as multiplication with parentheses. So this right here that I made up in this example means 2 times 5, and that would actually be in your multiplication step. I know it seems kind of confusing, but just know that the parentheses step, that P in the beginning of PEMDAS, signifies something like this or like this, where there is math to do inside of the parentheses. If it's just a number in the parentheses, like the example that I made up, it's not P for PEMDAS. Okay, one other thing I want to go over about PEMDAS before we start doing examples. I know it seems like a lot of details. People in this course come from different levels. Some people took like up to Algebra 1 in high school and they might need a review, and some people took up to pre-calc in high school and are just taking this as a fun course. So just kind of know your place, know what you understand, and be respectful to those people that maybe don't have your level of understanding or that need more time or whatever it may be. Okay? Luckily, this is a video, so if you want to jump around, you absolutely can. Just don't forget to look out for that code word coming soon. Okay, so that was my tangent. Now I'm going to get back to PEMDAS. So one last thing you need to know about these order of operations is that this M, D, and A, S are 1. So you're going to do multiplication and division in one step, and you're going to look for it from left to right. And then same thing for addition and subtraction. You look for it from left to right. So technically there's only 4 things you need to look out for in a way, because you do multiplication and division in one step and addition and subtraction in one step. All right, here we go with some examples. So directions just say for the following, evaluate the following. I wrote following twice. Following order of operations. So number 5, 3 plus 6 times 2. I have addition and I have multiplication. So only 2 operations to worry about here. Which one would you do first? Yes, sometimes I ask questions to the video knowing you will not answer me. Multiplication should be first. So 6 times 2 is what you're going to do first. That means the 3 plus has nothing to do with it. You're just going to bring it down. So 6 times 2 comes first because, like I said, multiplication comes before addition in PEMDAS. So you actually do that operation. 6 times 2 is 12. Okay, now there's only one operation left. You don't have to worry about PEMDAS anymore once you get to that last operation. 3 plus 12 is 15, and that's your final answer. Okay, moving right along. Next one, I'm going to just follow PEMDAS along the way. So the first thing I'm supposed to look out for is parentheses, and I have parentheses for this one right here. So I'm going to do that first. 3 minus 1 is 2. And you bring everything else down because you haven't done anything with it yet. Okay, after parentheses, the next thing you have to look for is E, which is exponents, and I have one of those as well. So 2 squared just means 2 times 2. You multiply your base by itself, the exponent amount of times. So 2 times itself twice is going to be 4 plus 6. And again, just to get you comfortable with your calculator, if you want to do exponents in your calculator, you're going to hit that 2. And then this is your exponent button. Okay, it's like a little upwards arrow. It's called a caret. You hit that, and that means 2 raised to the second power, and that gets you 4. So if you're not comfortable with exponents, plug it in your calculator and get comfortable with that caret button. Okay, and then 4 plus 6. Last operation, there's nothing to worry about with order there. I just combine them and I get 10. All right, number 7, moving right along. We do not have parentheses in number 7, so I move on to E, which is exponents, and I do have that. So 4 squared, you can plug it in your calculator if you want to, but it ultimately just means 4 times itself twice. So 4 times 4 is 16, and the rest of this just comes down. Okay, next thing I look for is multiplication and division. I do have multiplication for this one, and I'm going to bring down the symbol. So this 16 comes down, but I'm going to use that as a negative 16, just so you can kind of see we're getting into some negatives here. So negative 16 times 2 is going to be a negative 32. Another way you could look at it, just because negatives and minuses are very universal, is if you just think of it as a positive 16, that means this 16 minus would come down, and that's still 32. So either way, you get the same thing, but for this one, you just have to bring down the minus. This one, you did the math with the negative and got the negative anyway. Okay, so both good ways of doing it. Last thing we need to do is just subtract. It's the last operation, so I just do it. 16 minus 32 is a negative 16. Okay, moving on up to number 8. First thing I look for is parentheses, and I have some. 3 plus 6 is in parentheses. That gets me 9. And then the times 2 comes down. This is kind of an easy one. All you're left with now is multiplication. So you multiply those together and you get 18. So the big hang up, I guess, with this one, I said it was easy, but some people might get thrown off because it does have addition and multiplication. And typically you would do multiplication first, but P comes first, so you have to do the parentheses first. All right, next one I think has every operation, if not close. Yep, there's no adding, but everything else it's got. So I'm going to start with P, which is parentheses. So inside of the parentheses is 5 minus 2. I start by doing that. 5 minus 2 is 3, and then everything else comes down. This one's kind of tricky, so stick with me here. I took care of P in parentheses, so now I'm moving on to E, which is exponents. That's going to be this piece right here. 3 to the third power is 27. Use your calculator if you need to. And then everything else comes down. The next step after exponents is to check for multiplying and dividing in the same step. This one has multiplication and division. Which one do you do first? Okay. I know M comes before D in Pemdas, and this is kind of confusing, which is why it's a trick, but you always do multiply and divide in one step from left to right. And if I'm reading this from left to right, division actually comes first before multiplication. So I'm going to do this division first. So my 27 comes down. Negative 12 divided by 2 is going to be a negative 6. And then the times 1 comes down. See how that rule comes into play with the left to the right? Sometimes you do divide before you multiply. Sometimes you subtract before you add. It just depends on left to right order. Okay, next I'm going to multiply because I'm still on that same step of Pemdas with multiplying and dividing together. I'm just going to scoot that up here because I'm running out of room. So the 27 comes down, and then negative 6 times 1 is just a minus 6. Okay, now all that's left is subtraction, so I just subtract them, and 27 minus 6 is 21. Now, because math is a subject of practice, oftentimes I'm going to ask you to pause your video and give the problem a try. And the first one we're going to do for that is right now. So I'd like you to pause your video and give 10 a try on your own. Use Pemdas. When you start, we'll be going over it. So you should be coming back from your pausing now. We're going to jump right into P, which is parentheses, and that's this right here. So everything else is going to come down. And then I subtract those. 6 minus 3 is 3. Okay, next I have subtraction, addition, and division. The next thing in my Pemdas order that I would have to do with these three operations is the division. Okay, so the 5 minus 4 comes down. I have a positive 6 divided by 3, which is going to be a positive 2, so I bring down the plus 2. And hopefully you caught the trick for this one. All that's left is addition and subtraction, but when I go back up here, remember, I have to check them both at the same time and do them left to right. So when I go back to my problem, left to right, when I read it left to right, subtraction comes first. So even though A comes before S, they're the same step. You have to do them left to right. So you're going to subtract first. 5 minus 4 is 1, and I bring down the plus 2. And then 1 plus 2 is 3. So your final answer should have been hopefully 3. All right, moving right along to this thing called functions. We're going to do quite a bit with functions. It's honestly my least favorite thing to do in math, but it is a requirement for the course, so we're going to jump right in and try to make it fun. So substitution is another word for plugging in. That's probably a more common phrase. Plugging in for a variable. Okay, so substitution is plugging in for a variable. So when I ask you to substitute something in, like maybe substitute in 3 for x, you would plug in 3 for x. Okay, now the word plug in is significant because now we're going to talk about our input. Our input is the x value, or in other words, it's the number that's being plugged in. So what gets plugged in? Okay, plugged in for a variable is substitution. Your input is also known as your x value, and it's just the number getting plugged in. Lots going on with in. Now, when you have an expression similar to the first few examples we worked with when we had combining like terms, if you plugged in a number in place of the variable and then simplified using Pemdas, you would end up with an output. Your output when we're dealing with functions and for like the rest of the lessons to come is going to be known as your y value. And that's going to be the result, or in other words, the outcome. Okay, out for output. And it's basically the result or the outcome you get when you plug in that number and simplify it using Pemdas. Now going back to your Algebra 1 days, if you look in this box, it says normally an equation is written similar to the following example, which is y equals 2x plus y. Plus 7, sorry. Y equals 2x plus 7. However, as a function, this would be instead written as f of x equals 2x plus 7. So notice the 2x plus 7 and the 2x plus 7 stay the same. The only thing that changed is that y equals has now become f of x equals. And that is red, just so you know, that f parentheses x thing, oh, there we go again, is read as f of x. See, I threw myself off. It's read as f of x. So these are identical equations. The second one's written in function notation, that f of x idea that we just wrote about over here. Okay, so instead of y equals, it's written as f of equals. Why, you might ask? We're about to get into that now. It's really not a significant answer. I wish I had something better for you, but that's why this is one of my least favorite things to teach. Okay, so the directions for basically the rest of this page is determine, for the following examples, evaluate the following for the given value. So we're going to be working with substitution, or in other words, plugging in. So 11 says determine the value of the function f of x equals 3x minus 1 when x is equal to negative 2. So it tells me right here that x is negative 2, and there's an x in the function. What you have to do for this example is take that negative 2 and plug it in where you see an x. This function notation is not super significant. I'll explain why it's there at the end of this problem. I want you to focus on this part right here. So the 3x minus 1 is going to change up a little bit. Where I see an x, I'm going to substitute or plug in the negative 2, and everything else is going to come down. Now you're going to Pemdas that. I have multiplication. Remember, these aren't p. These are not parentheses in Pemdas. You don't do that first. That's considered multiplication. So 3 times negative 2, and I have subtraction. I definitely multiply first. So 3 times negative 2 is a negative 6, and then you bring down that minus 1. And negative 6 minus 1 is all that's left, so it's just subtraction. I don't have to worry about order anymore. You can plug it, you can plug it in your calculator if you need to, but negative 6 minus 1 is a negative 7. So to dig into the details of this problem, remember x is your input. That is the number that we plugged into the x in the expression that was given. Then we did some math and simplified it down and ended up with negative 7, which will be known as our output. So the input of negative 2 receives an output of negative 7. Every input will come up with its own unique output. Okay, now the part that's kind of insignificant is why this f of x is a thing. If you're plugging in your input, you would plug it in right here. So it would say f of negative 2 is how that would be read. F of negative 2. The only reason that that's there is because this whole thing that we just wrote, f of negative 2, is signifying to the reader that you're plugging in negative 2. That's its only significance. That's its literal whole purpose of being written like that, is it's telling you that your x value, or your input, what otherwise was an x, is now negative 2. So you're plugging in negative 2, that's your input, you get negative 7 as your output. Thrilling, right? All right, number 12, determine the value of the function g of x. So we've only worked with f. It doesn't matter if it's a different letter. You'll see, like, even this last one has an h in it. It's really no biggie. It's the same kind of idea. So g of x equals x squared plus 3x when x is equal to negative 3. So if my input is negative 3, I'm going to plug that in everywhere I see an x, and there's 2 x's in this expression. So I'm going to plug in that negative 3 in both places. So it's going to be negative 3 squared plus 3 times negative 3. And we're really getting comfortable with our calculator real quick. So in your calculator, and I'm sorry, there's so many different calculators you guys might have. This may or may not be true, but most times in your calculator, if you plug in negative 3 squared, it's going to tell you it's negative 9, which is incorrect. It is the one time your calculator is going to lie to you. It's deceiving you already on question 12 in this course. So to get the correct answer, if you need to plug these into your calculator, you must put parentheses around negative numbers that are being squared, like I just showed you in red. Okay, it's a big must. You have to organize your calculator so that that works. I don't know why it's a flaw in the calculator like that. It's unsure if you're squaring the negative. We absolutely are squaring the negative because that's our input. So you have to just inform your calculator that that's the case by putting the parentheses around it. Or think of it to yourself as -3 times -3, and a negative times a negative is a +9. So the correct answer is +9. If your calculator gives you that, awesome. If not, you have to put those parentheses around it, or just think of it like this. You can even plug in -3 times -3 in your calculator. It'll give you +9. And I bring everything else down, and I don't think I mentioned, but I started with the exponent because Pemdas. Next I have addition and multiplication. Between those two, multiplication has to happen next. So I'm just going to scoot up here. I'm running out of room. So I'm going to bring down the 9 plus, and I'm going to do this 3 times -3 next. 3 times -3 is a -9. Okay, now I didn't put the circle around this plus sign for this one because I wanted to show you this situation. When it comes up, it throws people off. If you have a plus and a minus, it's like adding a negative. Adding a negative is the same as just doing subtraction. Another way to read this is just 9 minus 9. Okay, they mean the same thing. 9 plus a -9 gets me 0. So that means that when -3 was my input for this specific g of x function, 0 was my output. Okay, so just to get you comfortable with substitution, I kind of ignored this fact for 11 and 12, but it's really going to come up now in number 13. So for number 13, it says using f of x equals x over 2 minus 1, determine f of -10. So above that, I'm just going to write that whole f of x idea. Notice, in place of x in this notation is a -10. This is the correct way of writing out these last two examples where they said when x equals whatever, but they're writing it using that function notation. X is equal to -10. So it's hidden in there. This is how you're going to often see it, so you really want to understand number 13 and the way that we're plugging this all in. It gives you that f of -10, which just tells you that x is -10. So in my notation right here, I have -10 over 2 minus 1. Now most of you probably are familiar with this, but I have two operations here. One of them is this fraction, and then I have subtraction. What operation is a fraction? Like, is it multiply, divide, add, or subtract? Good answer, it's divide. Hopefully you said divide, otherwise that's awkward. So I'm going to divide these right here. -10 divided by 2 is a -5, and I'm doing this division first because division comes before subtraction in Pemdas. Then I'm left with -5 minus 1, which is a -6. So when, see, I told you it's going to happen a lot. If you guys have an alternative, please email me and let me know. But I've been doing videos for a while now, and I keep doing it. I don't know. Anyway, that's my input for -10. When I plug in -10, I get -6, and that is going to be called my output. Right, the next two are kind of different types of function questions, 14 being very different, so kind of just put the rest of what you just learned in the back of your head for now. 14 says using f of x equals 3x minus 1 and g of x equals x squared plus 3x, determine the value of f of x plus g of x. So that's a lot. We're doing two functions in one, and what it wants you to do is add the two functions together. So f of x is 3x minus 1. So where I see an f of x in this expression, I'm going to plug in or substitute 3x minus 1. So I'm going to write 3x minus 1, and then I'm going to bring down that plus sign from the original given expression. I can't do much with this without plugging in what those functions are. You'll see how I can simplify it in a minute. Okay, next I have g of x. G of x is x squared plus 3x. So I'm going to bring that down as well in place of where I see g of x in the expression. So see how when this was given, I can't add anything. There's no like terms. There's nothing to do to it at all. Now that I have this expression, I can combine like terms and simplify this down. So the first term that I see is a 3x. See? And then the other term that I have with a like term of a x is this plus 3x on the end. So when I add those together, 3x plus 3x is 6x. And if you notice, there's no other like terms. A minus 1 doesn't even have a variable, and then x squared. So I'm just going to bring them down as minus 1 plus x squared. Now that is your final answer because nothing else can be combined. But what I'm going to show you really quick is the correct order. So the order of your terms is not significant yet, and it won't be significant until we get closer to like week 7. So you have a long time until this is significant, but it's better to get in good habits to start. So there's something called standard form. It's actually very easy, but it's the order that you want to put your answer in, and it's highest exponent, highest exponent to lowest exponent. Okay, so this one is not highest to lowest exponent form. That's what I need to do just to fix this. If you put this as your final answer, that's fine for now. You're going to need standard form later on in the course. That's why I'm showing it to you now. So the highest exponent here is my x squared term, so I'm going to write that one first. Then my next one is this x to the imaginary power of 1. So I'm going to bring down the positive 6x by writing plus 6x. And then that minus 1 is going to be my last term because it doesn't even have an x. Technically, it has an x to the 0. We'll get into that a little bit later as well. Okay, next question, number 15. It says using h of x equals 2x minus 4, determine the value of x if h of x equals 16. So this one is much different too than the previous questions that we've done, and we're not going to do a lot like this in the for the rest of today, I should say. It's going to come up in next week's notes though. So it's telling you that h of x is 16. If you're substituting correctly, notice the other question said when x is a certain number. I don't know why I keep doing that too. This one is not giving you, there we go. Whew. This one is not giving you an x value. It's giving you h of x. So you're going to plug in 16 where you see h of x. And it's kind of weird, but it's just what the substitution is telling you. That everywhere you see h of x, you're going to plug in 16. So I'm going to put the 16 here, and then everything else comes down. And then if you look, the way they worded the question is different too. It says determine the value of x. So you have to now solve this for x. This is what we're going to be doing next week. So if you don't understand what I'm going to do real quick here, don't stress about it. Again, we're going over it all next week. So to solve an equation for x, you have to get x alone by doing opposite operations. So I'm going to add the 4 to both sides. That'll get me 20 equals 2x. And then I have to divide by that 2. Get x equals 10. You might be thinking like, whoa, she's been going real slow and details, and then that just came out of nowhere. That's because, like I said, we're doing what I just did in red in next week's video. So as long as you understood this concept of plugging in the 16 where it's supposed to be plugged in for, you understood this question perfectly until we get into next week's stuff. All right, moving right along. Okay, so this course is called Functions and Modeling. All of the modeling we're going to be doing represents some real world scenarios. So you might be thinking like function notation is kind of silly to put into a real world scenario. We're just getting started. There will be some better examples to come in the future. Okay, but for number 16, it says you are given the function g of h equals 30h plus 7, where g of h represents grade on test and h represents hours studied. So putting some context to these variables. Don't freak out that it's not g of x. It's the same idea. They're just using an h instead. You can use any letter you want. The reason h is being used for this one is because h represents hours. So it just kind of helps you, kind of put into place. When you see h equals something, you know that that represents hours. Okay? So the first question is asking you to find g of 3. Now if you notice, 3 is in place of the h in my function notation. That's its purpose. It's telling you everywhere you see an h, you're going to plug in a 3. So the function is 30h plus 7, but I know I have to plug in a 3 where I see the h. So it's 30 times 3 plus 7. Now I Pemdas that by multiplying first. 30 times 3 is 90, and I bring down the plus 7. And then 90 plus 7 is my last step, which is just 97. So again, input is 3, output is 97. If it helps you to remember that input idea too with this function notation, the g of 3, notice the 3 is in parentheses, and it is the input. So I don't know if that'll help you. I always try to find some ways to help you guys remember things, especially with this function notation. Okay, B is a great example. So it says, interpret what g of 3 means in terms of the context situation. So the situation is talking about the grade on the test and hours studied. Your significant numbers here are 3 and 97. What do those two numbers mean in the context of the situation? Is it 97 hours? What is it? I'll give you a minute to think about it. Okay, so after 3 hours of studying, you will receive a 97 on the test. Look at the context here. H represented the hours studied, and they plugged in 3 for H, so that means 3 hours. The output is your G of H, and it tells you that represents the grade on the test, and you got an output of 97, so that means your grade on the test would be a 97. So that's what it means to kind of put it in the context of the situation. All right, part C and D, I'd never ask you these types of questions on a quiz or a test, so just keep that in mind, but it's something that you want to be aware of. So with the situation, when we're talking about H, that means hours. So part C says, what type of numbers could be plugged in for H? What type of numbers? Think about all the different kinds of numbers you've ever learned of. There's positives, there's negatives, there's decimals, there's fractions, infinitely many different types of numbers. What types of numbers could work for hours? I'm going to write positive. Okay, so the big idea here is that you can't really plug in a negative number because you can't study -7 hours. It's impossible to do that, so it doesn't exist in this specific context. So positive numbers only would work. You could have decimals, absolutely. You could have fractions. Those are all good. I'll say decimals are good. Like, it's a very open-ended question. It's just to get your mind thinking of the types of numbers that exist. So think about part D also now. What type of numbers could G result in? G represents grade. Can you have negative grade? Hopefully not. But no, that's a no. You can't have negative numbers represent your grade. You can have decimals. Those are possible. It's literally the same answer. So positive numbers only because you can't have negatives. Decimals are good. They're allowed. They aren't needed, but they can happen. So again, you won't see questions like that on a test or a quiz, so why on earth would I ask you questions like C and D? You have to be aware of that. So let's say we did the math up here and somehow we ended up getting like a -20. That should be a big red flag to you that you did something wrong. That's why you want to be aware of these types of numbers. If you get an answer that doesn't make sense in your problem, like a negative test score or negative amount of hours, those are unrealistic, and that means you mathed wrong. Yes, math is a verb. You did the math incorrectly somewhere along the line if you get an answer that doesn't make sense. That's what I want you to be thinking of there. Okay, moving right along. Domain and range. So adding 2 more vocabulary words because clearly you haven't learned enough already today. So your domain is just another word for your inputs, and remember your inputs are X values. Your range is just another word for your outputs, which represents your Y values. So these are all kind of synonyms of each other. Domain goes with input, goes with X values. Range goes with output, goes with Y values. Because it's kind of like 6 ideas to memorize and 3 of them are all synonyms, it's really only 2 concepts to remember. So if it helps you a little bit, if you look at the first letter of each word, R, O, Y, Roy might be a nice, easy way to help you remember that those all go together. That range goes with output, which is your Y values. They are all 1. So Roy will help you remember that. You can do the same thing with the first letter in domain, but it's a little inappropriate for me to say on a lesson. So if that helps you to remember too, go for it. Use that same way to remember it with domain. I'm just going to stick with Roy. All right, so number 17. It says you are given a function t of c equals 3c plus 20, where t of c represents time spent in traffic and c represents number of cars out on the road around you. So c is ultimately your x because it's inside of the parentheses. Remember, domain is inside. Okay, so c is essentially your x. Remember, X goes with domain. So when it says C represents the number of cars, that's going to be your domain. I want you to write that underneath the word domain, number of cars out on the road if you want to add. If you want to add that to your answer. The range is your Y value. Remember, Y is also known as, oh boy, that time I went up. Y is also known as your f of x. So that and y are technically the same idea. So when it's asking you for your range, it's asking you for this whole thing. T of c is like your f of x format. And that represents the time spent in traffic. So your range is the time spent in traffic. Once you finish up that one, I want you to actually pause the video again and try 18 on your own. When you come back, we'll go over it. Welcome back. All right, so you were given a function P of W equals 5W minus 9, where P of W represents profit and W represents the number of workers. So again, putting some real life context to this, but remember, X is always the inside or your input. Even though it's a W, it's inside of the parentheses there, which means it's your input. And W, being X, represents the number of workers. So your domain, since those are your X values, is going to represent the number of workers. Therefore, making your P of W, which is your range, the profit. Not so bad. All right, again, moving right along. We're going to get into word problems. Everyone hates word problems. They're not so bad. So interpreting mathematical situations is seen in real... Why can't I read that? Interpreting mathematical situations is seen in real-world mathematics every day. There we go. Just looking ahead a little bit. Okay. So... directions, create a function that represents the following scenarios. It's helpful to check that your function work after you write them. So that's huge. So let's get right into number 19. It says you currently have $780, that should say dollars, in a bank account that pays no interest. You withdraw $39 each week. Write a formula for the balance be in dollars in the account after T weeks. Okay. So don't stress about it for now. Let's just take it piece by piece. You currently have $780. So that's the number I'm going to start with because that's what I currently have. You withdraw money. I'm taking money away, or I'm taking it out of the account. That's going to subtract money from the 780 every week. So each week we're taking out $39. Here's where the variable comes into play. We have $780 flat. That's not going to change. But when you take money out each week, that number is going to change based on how many weeks you've taken it out. So the variable is going to go with the 39. And it's all because of this word right here. Okay. If you have something that says like each hour or per hour or anything like that, that means it goes with the variable, or in this case, the x. So those words, each hour, per day, whatever it may be, that means it goes with the x, because that number for this problem, that 39, changes for every single week that we have these withdrawals coming out of the account. Okay. Now that we understand that concept, I'm going to go into that second sentence. It says, write a formula for the balance B in dollars in the account after T weeks. So I actually made a little bit of an error here, but I hope it made sense to you with the X. It doesn't want me to use X. It's asking me to use T to represent weeks. So where I put an X, I should have actually put a T. Now think about that f of x notation. We're going to fill that out because it's asking us to create functions. We're going to get used to that function notation. So f of x is what we're used to writing. But in this case, my x is supposed to be a t, and it wants me to use b to represent the overall balance. So I'm going to put that b right here, and that's going to be my final function notation. You put the other letter on the outside based on whatever your x is, because x has to go on the inside. And this is your answer. Now, this right here that I start at the top where I said it's helpful to check that your functions work after you write them, just think about it. If you plugged in 1 right here to represent 1 week, you would have 780 minus 39 times 1, which makes sense. If you were doing this for 2 weeks and you plugged in 2, you'd have to do 39 times 2 and subtract that from 780, which makes sense because you would have withdrawn $39 2 times. See how you just kind of like do a mental check. You don't actually have to do any math. Just make sure that your function makes sense at the end. All right, number 20. You have $30 saved up in your bank account that gains no interest. You just received a job that earns $10 per hour and another that earns $11.50 per hour. Per. You plan to put all of the money from these jobs into this same savings account. Write a function that represents the total amount in the savings account S in dollars after H hours. So I'm not going to make the mistake again. It's telling me to use H in place of X for hours. So I'm going to do what I did in the last problem. I have $30 saved up. That's not going to change. That number is just going to be 30. Then we're earning money in this example. Specifically, I'm earning, so adding $10 per hour. So that per is going to go with my hour letter, which is H. And I'm also earning, so more earning, yay, love money, okay, plus for earns, another $11.50 per hour. And again, H represents hours. Now, because H is my X, ultimately, it's kind of like that same idea over here. You want it to be f of X, but since H is being used instead of X, that's the letter that goes in the parentheses, and the other letter, which in this case is an S, is going to go on the outside. So S of H equals 30 plus 10H plus 1150H. You can absolutely combine like terms. I'm not going to stress about it for you guys right now because it just makes more sense in the context of the problem that we leave it at 2 separate jobs. But normally you'd want to simplify it down. Okay, and every once in a while we are going to cross problems off. You guys are not going to do 21. You have a question very similar to number 21 in your homework. When you see that question, you are not going to have to practice it. Don't worry about it. If it's skipped in the notes, you can skip it on the homework. It will be skipped on quizzes and tests, I promise. If we skip something in the notes, you will not see it on a quiz or a test. So we're flipping right to the next page. Okay, getting into graphic representations of functions. So how to tell if a graph is a function is what we're going to write on this line. So next to the word graph, I want you to write vertical line test. You can also look at it as a VLT. But what the vertical line test is you have to draw vertical lines through your graph if those lines, oh boy, if they touch once, if they touch once, it is a function. If they touch more than once, it is not a function. So keep copying that down. Just kind of stick with me for a second. Pause it if you need to. The whole idea of like putting math into words, I really don't love it. I do it so that you can go back and read it later when you don't have me currently talking to you. The best way I think to go over that whole concept is to do some examples. So we're going to skip over that table line for now and just work on the graph examples by doing the vertical line test. So here's what the vertical line test looks like. Okay, if I draw vertical lines like the directions say throughout this whole graph, you can draw vertical lines anywhere on this graph. See how you can draw literally as many as you want, but notice how many times they're touching. I do want to go over a basic idea real quick. These lines right here are just your axes. Those don't count. It is this thing, also known as a parabola. If you know that already, that'd be awesome. That's what we're trying to see if it touches more than once. So the first vertical line I drew touched once, this one touches once, this one touches once, and I can keep drawing vertical lines. It's only ever going to touch it once, which means yes, it is a function. Okay, so yes, it is a function. So then moving on to the next graph, which would be number 25. If you draw a vertical line right here, notice it only touches once. Right here, it only touches once, but you want to check everywhere because if I draw a vertical line right here, 1, 2, 3, it touches more than once, so this one is not a function. Okay, so see the difference? Another way you can look at it, if you're at all interested, just really pay attention here if you didn't like the vertical line test. Another way to tell if something's a function is if you're able to follow it from left to right. So if you look at 22, see how left to right, it just goes in a nice smooth path. For this one, when you go left to right, it backtracks and then it continues forward. That's a big no-no. So that's another way to look at it if that's something that'll help you. You're not allowed to go backwards, just forwards from left to right. To tell if a table is a function, you're going to look specifically at the x values, and you're going to see that they don't repeat. Okay, it is not okay for your x values to repeat. It would not be a function. Okay, some people get that confused with x values or y values. They can't remember. What I tell my little high school students is that you never want to repeat your x's. It's a bad idea. No ex-girlfriends, no ex-boyfriends, don't repeat them, and that helps them to remember that you only have to worry about your x values. The y values don't matter. They can repeat all day long, does not matter. X values can't repeat. If they do repeat, it's not a function. So looking at the first table example, I'm just going to write x and y for my input and output. Number 23, if you look in your x column, because again, that's all that matters. Your outputs don't matter. X values can't repeat, and if you notice, they do. There's 2 repeating x values there, meaning that this one is not a function. Okay, for number 24, I do the same thing. I look at only my x values. -4, -2, +1 don't repeat. So yes, this is a function. Okay, Okay, do notice here as well that all the y values repeated, and it does not matter. Okay, so if you understand that x values don't repeat idea, awesome. Something that one of my students actually told me they learned in a previous math class I thought was very interesting is this is kind of like vending machines. So if you like fun ways to remember things, it's like a vending machine. So think about when you go to a vending machine, you put your money in and you type in your input. If you type in, let's say, a -2, you get a Kit Kat. Cool. Then you want something else. So you put your money in, you type in a 3, and you get a Snickers. And you really want another Snickers. So you put in your money again, you put in a 3 again, and it gives you a frickin' Reese's. That doesn't make sense. I don't know why I said frickin'. So when you have these identical inputs at a vending machine, when you type in a number, you should get the same output. You should get the same candy as a result. And that's why that's a no-go. I thought it was a really cool example. If that helps you remember it, awesome. If not, just pretend I said nothing. Okay, so at the bottom here, it says to provide a graph and a table below that do not represent functions and explain. So kind of like taking the question in a different direction. First, let's do the graph. So if it does not represent a function, that means that it does not pass the vertical line test, meaning it's kind of like number 25, where it touches a few times. My favorite example of not a function, and probably the easiest, is a circle. Because if you draw a vertical line through a circle, it's going to touch twice, therefore not a function. So to explain that, I'm just going to say it fails the vertical line test. Okay, for the table, remember, for something to not be a function, let's go back to this example. The one that was not a function had the repeating x values. So repeating x values are bad. I'm going to put repeating x values in here and then just call my output whatever I want. It doesn't matter. See, I'm plugging in 2 and I'm getting a Kit Kat, a Reese's, and a Snickers. That's wild. Okay, so my explanation for that would be x values repeat. Remember, that is bad, so that makes it not a function. All right, more with functions. I know functions are just a hoot. I love them too. As you can tell, I'm very sincere. So interpreting functions continued. Okay, remember the input is x and the output is y, or in other words, also known as f of x. So this is really like your y row, if you will. Okay, so 27 says use the function shown in the table to answer the following. F of 3. So we're kind of going back to when we first started with functions in this video. F of 3 stems from the f of x function. And what we were doing before is we were taking the value of 3 and plugging it in wherever we saw an x. So like let's say the function was 2x plus 7. We plugged in that 3 right there and we did some math to simplify it down and get an output. What's really nice about this table is it's already done the math for you. You just need to be able to find the output. So what you need to interpret so far with part A is that that 3 is an x value. So you go to the x row, which is this row right here, and you have to find 3. 3 in the x row is right here. When 3 was plugged into whatever function this is, it's not even telling us, it got an output or a y value of 9. So your answer is 9. No math, no nothing. All right, let's do that same thing again for B. So part B is giving me an x value again because it's inside the parentheses. It has to be my input. And the input is 4. So 4 is right here. Its output is 16. Now this next example might kind of clear up why people might get confused on a question like this. So for part C, it says if f of x is 4. So we're not looking at the x row anymore. We're looking at the f of x row. And we're trying to find 4. So 4 in the f of x row is right there where I circled in green. And it's asking me what the x value is. So I'm going to say that for an output of 4, my input is 2. It's the same type of question. It's just going backwards, but really the same kind of question. So same thing for the next one. If f of x is equal to 16, so I look at my f of x row, I find 16, which is right here. It's asking me what is x? X is going to be 4. So what's really kind of cool is that B and D go hand in hand. They were asking the same question but backwards. If x is 4, y is 16. If y is 16, x is 4. This next question is probably going to be your favorite one of these notes. Ready? Not doing it. Okay, so you also have a question like 28 on your homework. Don't do it. You will never see a question like this on a quiz or a test, so don't even bother practicing it. If you don't learn it, I'm not going to quiz you on it. All right, moving right along. Number 29. Reading and interpreting graphs. So being able to read and interpret a graph is really important in mathematics, especially when you get into learning how to make graphs. So this one's a real life scenario. It says Kevin heads out to school by foot. His distance from school in blocks is given as a function of the time in minutes he has been walking. This function is represented by the graph below. So just some graph facts. This is always going to be your x-axis, and this is always going to be your y-axis. Y to the sky, it's the one that points up. Okay, it's telling you that Kevin is heading out to school by foot. So if you look at what's happening here, your x-axis represents minutes, so time is going on the more the graph goes towards the right. Then your y-axis is representing your blocks from the school. So look at where he starts at 0 minutes, which is when he initially starts walking. He's right here. And then he goes down. The graph is going down, 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 which means he's less blocks from school. Where is he walking? If he's going down on this graph and becoming less blocks away from school. Okay, it even says it in the directions. He's walking to school. But that's how it's signified in the graph, is by, like, he's starting at 20-something blocks from school, and then after a few minutes, he's 10 blocks from school. That means he's getting closer to the school building, aka he's walking to school. Okay, so let's start out with these questions now that we kind of have an idea of what's going on here. Part A says, how far does Kevin start off from school? That's that red dot that I graphed up there, but be very careful with this. Your scaling is a little bit different. This is not 1, 2, 3, 4, 10. That's not how that works. Okay, these are actually going up by 2, 4, 6, 8, 10. They're counting by twos. Your x-axis, 1, 2, 3, 4, 5, that makes sense. These ones are counting by ones on your x-axis, but your y-axis is going up by twos. So if this is 20, that would make this 22. So how far does he start off from school? Would be 22 blocks. Okay, what is his distance from school after he has been walking for 4 minutes? This is a great example of an input-output situation. 4 minutes is your input. You just have to find that on the graph. So 4 minutes on the graph is right here. You have to match that up with how many, what his distance is, I should say, how many blocks he is from school by connecting it to the graph. So I'm just going to draw a line up until I hit the graph, and then I'm going to scoot that line over right here. That's how many blocks away from the school he is after 4 minutes, and that's going to be 14 because remember, we're counting by twos. So he is 14 blocks away from the school after he's been walking for 4 minutes. So part C is kind of weird. It says explain something that is happening between 6 and 9 minutes. So first, 6 minutes is right here. 9 minutes is right here. So if I follow those up to the graph, it's really this section right here that I just highlighted in green. It's flat. So between 6 and 9 minutes, time is moving, but his distance stays the same. Right here, he's 10 blocks from the school, and right here, he's 10 blocks from the school. So what's happening between those 3 minutes? There's so many creative answers you can come up with, but they all have to be along the lines of he stopped moving. Okay? Whether he really had to pee and stopped at a gas station, or he saw a friend and stopped to chat, or he can't text and walk at the same time, so he had to stop to text real quick, had to tie a shoe, and it took him 3 whole minutes. Whatever it may be, he stopped. Time went on, his distance didn't change. Okay, next one, describe what might be happening between 9 and 11 minutes. So 9 minutes is still right here, 11 minutes is right here, so it's talking about this part of the graph where it starts going up again. Remember, we talked about how down means he's getting closer to the school. So if you look at these numbers here, at 9 minutes, he was 10 blocks from the school, and at 11 minutes, if I draw that line over, he was 12 blocks from the school. So he's walking to school, but he was walking in that moment for those 2 minutes away from the school. So that's ultimately what happened. He walked away from the school, or in other words, he turned around. Okay, but again, you can get very creative with these answers as well. I've heard answers before, like he realized he dropped his $100 bill out of his wallet and turned around and went to go get it. His friend was a couple minutes behind him, so he turned around to meet up with his friend, and then they continued walking together. There's infinitely many answers you can come up with if you want to be creative. You don't have to. Getting back to that input notation, D of 5. Notice 5 is inside of the parentheses, which makes it your input. So that's going to be your minutes spent walking or looking at your x-axis. So I find 5, which is right here, and it's asking me what the output is. So essentially, how many blocks is he from school after 5 minutes? So I draw my lines, and it falls on 12. So my output's going to be 12. And then the next one's a little bit tougher. Okay, but what is x when d of x is 6? So d of x is his distance, which means I have to look at my y-axis. That's my d of x, and it's asking when it's 6. So 6 is right here. So I follow that all the way over to the graph, and now I need to find the x value that matches that, which is right here. And that's going to be 13 minutes. So your x value is 13 minutes. All right, this last page will go very quick. We're not going to do part G, so you can just cross that off. Number 30. Can you believe we've already done that many questions? Woohoo! So interpreting graphs continued, just so you don't get deceived by any graphs. So 30 says, observe the differences in the graphs below. They have the same y-axis number of shampoo users, but the graphs look significantly different for 2007 and 2008. If you look, it says the graph on the left looks as though the number of shampoo users is much more in 2008 than it was in 2007. Thoughts? So just kind of look at the two graphs for a minute. I'll give you some time to think about it, and you can pause it if you need some more time. But why might it look so drastically different in the left graph versus the right graph? So pause the video if you need some more time, but hopefully you're looking right here at your y-axis. They're different. That's the only part of the graph that's really, really different. Okay, so this graph over here, the y-axis is only showing you between 81 and 86. So it's literally like just showing you this part of the graph. Which is kind of crazy. So that's why it looks like such a big difference, because right here, it doesn't look so big, but when you zoom in, it looks like a much more significant change. So this graph is zoomed in. certain companies that want to show drastic results for stuff like this, if they show a graph on a commercial or even in like an article or something, they might use this to their advantage because some people don't really look at your axes. They just look like, wow, it's almost like twice as much used it in 2008 when really it's only a difference of 3 people. It looks like so much more. It's kind of like cheating. It's deceiving your eyes. So the graph is zoomed in. Scales are different. And then the last question we're going to do is kind of the same idea. Okay, they're both adoption graphs, number of pets, cats and dogs. The first graph looks more significant, but it's literally the same kind of question. The scales are different. This one starts at 50, so it's only showing you this portion of the graph. So this one is once again, it specifically asks, are they different? The answer to that's actually going to be no. And if not, why do they look different? It's because their scales are different. Or in other words, because this one is more zoomed in. It's focused on what I just squared off in that right graph. Okay, if you have any questions about what we went over in this video today, please feel